All right, let's get started again here. All right, so how this works with these valves, these poppet valves, open and close, they're timed directly to the crankshaft. There's a gear on the back of the crankshaft, and that gear drives all the other gears that connect everything together inside the engine. So this little gear, it's only about this big around, you'll see it. I'll tell you what, everybody bring your tools in tomorrow. We'll have you pull the accessory case off, and that's going to explain a couple things to you. It's not going to take you but 10 minutes to get the whole darn thing off of there, but it's going to explain how the camshaft is timed to the crankshaft. So there's a number of gears on the back of the engine that are all tied together. They don't slip out of position, they don't move, there's no variation on them. They fit together. There's going to be two that are going to be marked like this. There's going to be a little mark so that you use the low spot between them. There's going to be another gear that's got a mark on it. You use a high spot, and they fit together just like this. If you put it all together right, everything is positively timed. So all of these gears mesh and align together just like everything is supposed to work. Now, it's beyond me. But I found engines in the past, the engines never really ran very well, and the owners put up with them. They wouldn't meet the RPM that they're supposed to put out, and people lived with it, and I don't know why. The only thing they had to do was pull the engine out. You can get the engine out of an airplane pretty quick. Pull the engine out, pull the accessory gearbox off the back end of the thing, and reset the gears to where they belong. You'd be surprised what the difference is. So if you have an engine that's timed 1/2 out on a gear, it can kill an engine. An engine that ordinarily would make 2,700 RPM is only going to make 2,500 RPM, and that's huge on an airplane. You need those extra couple hundred RPM to develop full horsepower from the engine. Why people put up with it, I don't know, but they do. All right, so everything is timed together. I'll ask Lana to have you guys pull your accessory section off tomorrow night. Probably only 8 or 10 bolts that come on. You'll be able to see how that works. All right, so the engine's going to draw air and fuel into the intake manifold. You're going to have a carburetor, or you're going to have an injection servo. If you have an injected air engine, the injection system is going to provide fuel at the port. It does. It's not like an automotive engine that drives that puts injection directly into the cylinder. It is a port injection. So there's a continuous flow of fuel blowing into the intake port, and it doesn't mix with the air until right before it goes past the valve. So that air is rushing like crazy past the valve. As soon as the valve opens, it picks that fuel up, mixes with the fuel, and then is carried into the cylinder. All right, so into the chamber before top dead center on the intake stroke is when it begins to move, when that valve begins to open, and that valve is going to close. The intake valve is going to close at after bottom dead center, a few degrees after bottom dead center. I have a little project for you. Once we get that far, I'll give that over to you. So you're going to be drawing, marking up a chart so that you know when the valve's open and when the valve's closed. It's kind of an important thing. The exhaust valve is going to allow the combustion out into the tailpipe, into the exhaust system, and overboard from the engine. It's going to open from before bottom dead center on the power stroke. So before the piston hits all the way at the bottom, that valve is going to begin to open. Now, because of the geometry of the system, that valve's not going to move very fast initially. Until the lobe on the camshaft gets all the way up, it's not going to push the valve all the way open. So it's going to be opening little by little by little, and then it'll start moving faster, and then it'll start closing again. So it's going to open from before bottom dead center on the power stroke, and then it's going to close after top dead center on the intake stroke. So that period of time, you're going to have two valves open just for a short period of time. You see that on the chart. And that's called valve overlap. Write that down right now. Valve overlap. And both the exhaust valve and the intake valve are open at the same time. Valve overlap. Again, the reason for this is if you have the exhaust valve open a little bit, when the intake valve begins to open, it allows the air and fuel to flow into the combustion chamber a whole lot better. It propagates the flow. Now, intake systems are kind of a funny thing. You'd think that valve would close, everything would stop, but it doesn't. Because all these molecules of air and molecules of fuel are running down a runner. They're running through a pipe through the inside of this engine. And when they do, they get a certain amount of momentum up. And that sort of helps to supercharge the engine a little bit. That energy that's stored in that fuel, when that valve opens, it rushes right in because of the momentum of the air and the fuel. So having both of those valves open at the same time allows better ventilation. It allows more air and more fuel to enter the cylinder so that you have more air and more fuel when you ignite it, and you get more horsepower out of the engine. Now, think about this for a second. The piston goes up, the piston goes down. Does it come to a dead stop? The crankshaft doesn't go to a dead stop. Does the piston go to a dead stop?
Yeah.
Yeah, it's reversing direction.
There's some little hang time at the bottom and at the top.
It's hang time, right? But the piston is dead stop. All of that is in the linkage. This is going to continue the movement. The piston comes to an absolute dead stop, top and bottom. So we can use that little bit of extra time down there to allow the engine to ventilate a little bit better. Piston comes to an absolute halt at the top and the bottom, reverses course, and goes the other way. What you're going to find, and I'll probably talk about this next week when I'm talking about cylinders, is most of the wear in the cylinder is going to occur at the top of the cylinder. That is to say, in the combustion chamber end of the cylinder. And the reason for that is because, one, you're scraping oil away from the rings at that point, you're pulling it back down off the cylinder wall, so you have less lubrication there. You have air and fuel in that area. That fuel tends to wipe or erode the lubrication in that area. You also have very high temperatures because of the combustion. The cylinder head is pretty hot in that area, and that piston is stopping, dead stop, turning around and going the opposite direction. So those rings are wearing the cylinder at a greater rate than it does on the other end of the stroke. So if anybody asks you where the greatest wear area is, it's at the top of the stroke. And so when you go looking and measuring in your cylinders, and you're all going to be measuring your cylinders once you pull them off, you're going to find that the greatest wear is going to be up in that top end of the cylinder. The other thing is, because of the movement of the connecting rod, as the crankshaft turns, that rod is laying back and forth one way or the other. It tries to tip the piston slightly at the top of the stroke. So that piston is being thrown against the cylinder, or it's trying to be thrown against the cylinder, and that also helps to exacerbate the wear in the cylinder. So all those little things kind of add up. Now, it's not a lot, but you're going to find the greatest wear in that area on the cylinder. Okay, so ventilation, you probably want to write these down. It's going to use up about 440 degrees. Remember, we're talking about 720 degrees of rotation. So ventilation, that is to say intake and exhaust, is going to use up about 440 degrees of that rotation. Compression is going to be about 100, 120. The power stroke is going to use up about 100 degrees to 150 degrees of that. Once that piston gets down so far, you stop losing any real usefulness of the power stroke. And the compression buildup is about 40 to 60 degrees of that. So you don't get much real compression on the compression stroke until that piston really starts moving up. So if the piston stops at the top and the piston stops at the bottom, Where is the piston speed the greatest?
In the middle.
Right in the middle, 90 degrees. That piston speed will be its highest at 90 degrees after top dead center, before top dead center, before bottom dead center, however you want to say it. 90 degrees of its travel, that piston speed is going to be the highest. So the ignition timing, we know when that has to go off. That has to go off just a few degrees, a little bit before top dead center on the compression stroke, so that everything is ignited. The pressure buildup occurs 15 degrees after top dead center on the power stroke. So all this is driven off of the valve timing. The valve timing is run by the camshaft. The camshaft also sets the ignition timing. Once you pull the accessory case off tomorrow off your engine, you'll see that. Now you can see, think about the position of the connecting rod relative to the crankshaft and the piston, right up around the top dead center area. Even though the pressure starts building pretty high, you're not getting much of a push on the crankshaft because of the mechanical leverage. There just isn't any at that point. Until you get out there about 15, 20 degrees, right around Mr. Powell's magic angle, and then you start getting some leverage on the crankshaft all the way down to where it's running toward the bottom. Okay, so right about here is where you're going to start to have good mechanical advantage on the crankshaft. And that's because the connecting rod is translated over, it's kind of twisted over to the side a little bit. So you have those two pivot points about the pin in the piston and the crank pin on the crankshaft. That thing, again, if it was straight up and down, you wouldn't have any movement of that crankshaft whatsoever. So we have to have that crankshaft tipped over slightly so that it's able to continue to turn. Everybody, we're going to go back over this. You're going to be so tired of hearing this stuff. We're going to talk about crankshafts. We're going to talk about camshafts, gear trains, pistons, valves, all of that stuff in the next few weeks. But we're going to talk about those each individually. But you kind of have a sense of how this chunk of iron works here. Anybody? Mm-hmm. Start to get it little by little. Yeah, it's not that difficult. And the other thing too is go outside and turn that handle on that thing. Okay, as you're standing in front of it, turn the handle counterclockwise. That's the direction you want to turn it. All right, so there's some different configurations. They come in a lot of different shapes. Most of the engines are like what you see outside here. They're either going to be radial engines or they're going to be opposed engines. Gasoline engines come in all kinds of different configurations. There are aircraft engines where they are all in a single row, 4 or 6 in a row. There are engines that are radially arranged around the crankshaft. We have these, we have everything you can imagine. What I want you to know, you don't have to write any of this stuff down. In fact, please don't, we're going to buzz through it pretty quick. But know that there were a lot of engines built over the years. A lot of these were European designs, some American designs. They didn't work out for a number of reasons. They were expensive to build. They couldn't build them quick enough to satisfy the market. In some cases, they were built during the world wars, And they just couldn't produce these things, so they didn't work out for one reason or another. Either they weren't reliable, they were too heavy, didn't make enough horsepower. But know that they came in all these different configurations and more. Okay, so some of them have multiple crankshafts, they have fixed crankshafts with the cylinder and the engine case spinning. That's called a rotary engine. They were rigged with horizontal or vertical crankshaft. That would be like a helicopter engine. Still a lot of those around. I'll tell you when to start writing again. So there's one called a Wankel cycle. It was developed by a German inventor. It's semi-rotary. You'll see how it works in just a second. Not too many of these in aircraft engines anymore. They were used for a long time by the experimental home build or amateur built guys, and they worked okay. The trouble is they used to wear themselves out pretty quick. I'll show you the seal. They used to have a seal in there, so they don't have a piston, they have a rotor in them. And they make a lot of horsepower. They can be stacked up like pancakes to get more and more and more horsepower out of them. But know that they're kind of heavy engines. You get to the picture. This doesn't make much sense. I'll show you. Okay. So here's kind of a diagram of this. You got a rotor. It's inside two centrifugal openings that are attached to cut into each other. It has a shaft, and this rotor, this triangular shaped rotor here, spins on that shaft. These things shake a little bit, they're not particularly smooth. Two spark plugs up here. So what happens is you ignite the air-fuel mixture, and this thing is going to be spinning around here. Oh wait, it goes this way. As it does, it turns. Oh wait, no, it's going to turn clockwise, I guess. So this is the exhaust here. This is the exhaust being dispelled out the exhaust pipe. This is the intake here. Okay, that makes sense. You've got the intake mixture being squeezed. That rotor comes around and ignites it. Now see how that works? Kind of a goofy thing. Yeah. They work pretty good, actually. Mazda built those for years, put them in cars. Their R series cars always work very well. They were designed for torpedoes. And the reason they used them for torpedoes was because they could make a nice little round engine that took up all the space in the torpedo. It fit in there perfectly. Worked perfect. They used air. An air tank to feed it air and allow it to breathe. So the rotor's going to spin, it has some oscillations, so the rotor kind of moves around in a circle. Funny little things. They work pretty good. They stack them up, each bank of rotors, and I've seen them stacked as high as 6 and 8 at a time. They'll build a couple thousand horsepower if you put enough of it.
How was it? Like separate chambers or something?
Yeah, let me go back here. So each one of these, what you see here is a cross section of one bank. So it's about this thick, kind of shaped in a round circle. Inside of it is this. So you can stack them up. You can put one bank next to another bank to another bank.
Okay.
You just have a shaft that goes through it. So each rotor is contributing. It's like another cylinder, sort of. Yeah, each one is contributing to the other.
Have you ever seen them put them in the 177s?
What's that?
Apparently Cessna put some of those rotaries in 177s.
Yeah, and it just didn't work out. Oh, let me show you why it didn't work out. Good, I'm glad you said that. At the end of each one of these tips, as you might suspect, there has to be a seal. And if there's no seal there, then the exhaust gas escapes over to the intake side, and the intake gas escapes into the inlet, and it turns into a messed up deal. Well, Mazda for years had a problem with these seals. They couldn't get them to seal. That's what the problem was. The seals wore out prematurely. They kind of figured it out in the end, but the engines kind of lost their popularity. But what they did was they built these seals out of carbon, and they worked pretty good, but then all of a sudden they failed. And so you never knew if you had one fail or you had all three fail, but you had to tear the engine down and replace those seals. And so, as you might guess, people were not happy about having their car engine torn down every 12 to 15,000 miles to have these seals put in. It was an interesting design. It is an interesting design, it's a good design, but once those seal problems were taken care of, then all of a sudden it became viable. But like most things, consumers kind of, it gets a bad name, and all of a sudden nobody wants it anymore. That's kind of what happened.
Would they be more gas efficient at all in any sense?
Actually, they burn a lot of fuel. You remember when we were talking about the two strokes, you lose a little bit overboard all the time?
Yeah.
These would also do the same thing. You always lost a little bit of fuel overboard. So they had some emissions problems also.
They have high specific horsepower, but low efficiency.
Low efficiency. Okay. Let's see. So you don't have to worry about this too much. These are just some things that I came up with. I just want you to know they're out there. They're on gasolines, usually alcohol also. They're not particularly efficient, but for some things they work okay. Now diesel cycle, I want you to pay attention to this because we're going to come back to the diesel cycle at some point after we finish the engines, the gasoline engines. And the primary difference is the compression ratio. So when we compress the air even more, what's going to happen to the temperature inside the cylinder? What's going to happen? So if we've got 8.5 to 1 compression ratio, so if we take this much air and we squeeze it 8.5 times, so it's going to squeeze it into a tiny little ball, the temperature is going to go up on that air, right? But if we start squeezing it up to about 14 or 15 to 1, what's going to happen to that temperature on that air? It's going to be higher? Yeah, it's going to be much higher. So we're going to be able to introduce fuel into that air and it will begin to combust as soon as it's introduced. So we're going to use high compression. This is also known as a compression engine. So diesel fuel is going to ignite at a lower temperature. The trick is to keep it burning. So it has a flash point about 300 degrees. When you have an engine that's warmed up, fully warmed up, what's going to happen is the engine is going to contribute heat to the air that you're already squeezing. So you're going to squeeze that air on a cool day, 70-degree day. It's going to go up to probably about 200 degrees. But because the engine is already warm, it's contributing to that heat. You're going to start at 200 degrees. You're going to squeeze it up 13, 14, 15 to 1. That's the low end of the diesel cycle. When you do that, now that temperature is going to scream up to about 500 degrees inside that cylinder. So as soon as you add fuel to it, it's going to begin to combust. So we talked about detonation, right? Earlier, talked about detonation. This is going to be a controlled detonation is what it's going to be. So we can meter the amount of fuel going into the cylinder. So we just sort of spit it all in at once. We can kind of, it goes in pretty darn quick, don't get me wrong, but we can kind of meter the amount of fuel that goes into the cylinder, and we can send it into the cylinder when we want it to, so we can time when that fuel begins to burn. So on a spark ignited engine, we do that timing by changing the spark. When you have the spark hit that stuff, hit the fuel air mixture, right? On a diesel engine, we're going to introduce the fuel at a specific time. The only thing that's going to be squeezing is going to be the air. Yeah.
I thought diesel had a higher flash point.
Then the flame point? Flash point is going to be lower, but to keep it running, there's a big spread between the flash point and the flame point. And that's where we're going to use that extra temperature to keep it burning in there. So here we go. This is going to be a compression engine. You still have 4 strokes. Still have a compression. You have the power stroke, right? The power stroke. Then you got the exhaust stroke, compression power. The ignition is going to be part of that power stroke now because it moves over further because the combustion happens so fast. Combustion happens so fast, that's why you hear that knocking on diesels. You don't know what a diesel engine sounds like, right? That's why you hear it, because that fuel burns so quick and the compression is so high, that's that rattling sound that you hear. That is a combustion event. And these engines typically have to be built quite a bit stronger. to handle that pressure. But with modern metallurgical techniques and manufacturing, they can do that. So it used to be everything had to be made out of cast iron, but not so much anymore. There's getting to be a lot of aero diesels out there now, and we're gonna dive into those at some point. All right, now there's some question as to whether or not the diesel came first or the gasoline engine came first. Nobody really knows because they were both developed about the same time. Diesel starts in about the 13-to-1 range of compression. About 13-to-1. Any of you have pseudonyms?
Could you? I'm sorry. Could you?
How do you know what Sky Active is? Anybody? Sky Active. It's a really interesting concept. In aviation, I could see aviation will start going that direction at some point. It's running up around 13 to 14-to-1 with gasoline engines. Yeah.
Could you explain the compression rate? What that means?
Sure. The compression ratio.
Yeah.
So you hold your bottle up there. So that's one. If you take 13 times that, that's 13. Okay, 13-to-1. So if you take, or let's try it the other way. So that's 13 there. If we squeeze that down 13 times to 1, what that's going to do is that's going to compress that air down to that amount. So it's a measure of volume. That's what it is. So if he's got 13 in that bottle, we squeeze it down to 1/13 of that. That's what it's going to be inside that bottle. And that's what we're going to do with the piston. Remember, the piston is going to draw it in. You're going to have 13 in there, and we're going to squeeze down 13 times. And that's what's going to be left in the combustion chamber. 1/13 of what you draw in. And when you do that, when you compress that air, that temperature is going to go way up. So Sky Active, it's a little bit different than the system that we're using. What they do is they put a weak mixture in there. It doesn't have a lot of air and fuel in it. And they begin to combust it. They begin to burn it at top dead center. So their Powell's magic angle is going to begin to occur at about top dead center. And then it's an injected engine, so they add a little bit more fuel to it as the piston begins to move down. So they get the piston moving, and then they add just a tiny bit more fuel to it. So it's actually 2 squirts of fuel that is burning along the entire travel of the piston. So they electrically spark the second part. Remember, they're using the diesel cycle for the first part, and then they're going to electrically ignite the second part. So that gives you a longer, smoother pulse against that piston. And they can do it at compression ratios about 14, 15-to-1 with gasoline. Yeah.
So why do people say that diesel engine is more efficient than gas?
It runs at higher temperatures. Not all of them, but the ones that we use run at higher temperatures. And so so if you think about it economically, the fuel is cheaper. You get more bang for your buck out of fuel. The fuel is heavier than gasoline. You end up with more power per pound out of that fuel. You end up with more torque. And if you have more torque, you can, if you're using it on your truck, you can haul bigger weights because of the extra work that it does. In an airplane, you can swing a bigger propeller. You have a propeller that has more pitch in it, so the airplane moves faster with a smaller engine. It's safer to ship around than gasoline. Gasoline is very flammable. Diesel fuel is less flammable, or turbine fuel. So it has all these different things going for it. In some parts of the world, you can't get aviation gasoline. All you can get is some crappy gas, maybe, but most parts of the world use diesel or jet fuel. So that's some driving reasons for it. Yeah. Okay, so when we inject it into the engine on a diesel, it tends to explode. That's where you get that noise from in the diesel. It makes that hammering sound. It goes off so fast that it pounds against the top of the piston. Pistons are built to take it. The cylinder heads are meant to take it. The cylinders are all meant to take it. So it really doesn't have any bad effect on the engine, other than sounding kind of funny. Yeah, it sounds like a rod. Okay, so about 13-1 for diesels, where diesel territory starts. As you might guess, there's going to be pretty high chamber pressures, cylinder pressures in the engine. That last line down there, I let you put that in there. What they did was quite a number of years ago, General Motors built an Oldsmobile, and they used a stock block 350 Chevy with aluminum heads. And the heads were okay, but it ripped the studs out of the block because the pressures were so high. If any of you get a chance to buy one of these in pristine condition, you ought to do it. They become collector's cars. Generally, you find them with old people, 90-year-olds or older, owning these things. They've been in a garage all their life. Cars that they probably sold for a couple $3,000 when they were new. They're probably worth about $25,000–$30,000 a pop now. Nice. With General Motors diesel. They were pretty heavy, made out of cast iron with aluminum heads, but they most of them tore the studs out. There was so much chamber pressure. Okay, so here's the diesel cycle here. Here's the diesel cycle. Instead of having a spark plug here, we've got a fuel injector. Now this is direct injection into the cylinder. This is high pressure, timed direct injection. So, so we're going to have this thing. It's going to operate just like the other ones. It's going to draw air in, no fuel, just pulling the air in. You get more air in, and then add fuel to it. You have more air and more fuel in the cylinder, so you're going to have a little bit better efficiency that way. Okay, so the intake valve is closed. We're going to compress it some more. The timing is going to occur about top dead center or after. If you had the timing too far before top dead center, what would happen? Because this stuff goes off very, very quickly. It goes off faster than a spark ignited engine. If we added fuel at this point, what would happen to the engine? Try to run backwards. Exactly right. So we're going to ignite the fuel. We're going to put the fuel in it just about top dead center. We're going to put it in a higher pressure, much higher pressure than the chamber pressure, and that's going to allow that fuel to flow into the cylinder. As it goes in, it begins to combust. All the rest of it's the same. Okay. All the rest of it's the same, except we're injecting fuel. That is the ignition event on this engine. Now, they're not used in aircraft, so we're going to find out that that's not really a true statement. They're good for high torque. As I said, you can put more propeller on an engine. You can put more pitch in a propeller, where you can put bigger props on, more blades on the propeller. The aircraft will go faster. One thing that it does, because this fuel gets to be about 6.5–7 pounds per gallon, where aviation gasoline is what? About 6. So the fuel is a little heavier. You start losing your payload just a little bit because of that. Okay, diesel fuel is pretty darn safe besides that. Now, diesel fuel doesn't react with seals in the same way as gasoline does. It will attack seals. Some seals, gasoline will attack other seals. And so you have to know that if you have an aircraft that's been converted, all those seals in the system, the entire system has to have been converted as well. Turbine fuel is the same thing. So most aircraft that use diesel fuel also use turbine fuel. Turbine fuel will attack seals that are made for gasoline, cause them to swell up and begin to leak. So know that if you have an airplane, you encounter one of those airplanes, and some book says to use this seal, and it's for a gasoline engine, you better know that you better use the right seal because you might have turbine fuel in this thing. All right? So know that you could have a problem between the crossover on these. Okay. All right. So let's see here. So we talked about that. So here's an airplane here. This is a Diamond Twin Star, twin diesel engines on this airplane. These particular engines were built by a company called Teeler. in Germany. It was a Mercedes-Benz block that's been aeroized. They put aircraft equipment on these blocks. They originally were cast iron blocks, but they've gone to aluminum blocks. Keeler is out of business now. They got some kind of shaky business practices, but there are a number of companies making engines, diesel engines now. But I wanted to show you an airplane that has diesel engines on it. Nice airplane. They're beautiful to fly. You probably already know. You got a customer or a couple customers with these up there gives.
It's fun to work on.
Yeah, nice airplane.
You know, except for that one time when I didn't have gearboxes and nobody could fly them for like 2 years.
Yeah,
There was that little oops.
there's a
Yeah.
little problem there. Yeah, one of the things about a diesel that Dana's referring to is that diesel engine, as you might suspect, has a pretty hard hit every time the cylinder goes out. It has a big thump. So the more cylinders you have, the smoother that power impulse is. If you're working with a 4-cylinder engine or a 6-cylinder engine, it's going to be a different story than with an 8-cylinder engine. And so remember, every time that prop goes around twice, all of those cylinders have to fire. It's the same thing with a diesel. And so if you have a 4-cylinder engine, every 90 degrees of movement or every 180 degrees of movement, you're going to have a piston fire. And these things hit really hard because of the compression and the power that they're making. Well, think about the power impulse as it shakes down through the crankshaft and it goes out toward the prop. Most of these things now have composite propellers on them, and composite will absorb a lot of the power impulse. But the trouble is these engines run at very high rates of speed. So remember I said that these little gasoline engines run about 2,700 RPM. These things are running about 3,500, 4,000 RPM. So they're smoking along pretty good. And every time they hit that propeller, you have to reduce the speed down so that the propeller doesn't turn too fast. And so when you do that, there has to be a gear reduction box in there. Now, not all of these diesel engines have gear reductions in them because they don't need them. They run at slower speeds. This particular engine does, and it would beat the guts out of this gearbox. So every 500 hours, there had to be a gearbox inspection conducted, and that was fairly expensive, plus the labor and the downtime on the aircraft. So this was something that it was kind of a toy for rich guys. They're beautiful airplanes, they fly nice, but it is kind of an expensive piece of equipment. A lot of flight schools own them. The flight schools had great luck with them, and they still do. But it's become part of their maintenance plan to do the gearbox inspections on it. So know that you've got that also enters into it. Okay, so the constant flow cycle engine, you don't have to write any of this down. You'll get this in the turbine. It's known as a turbine engine. So in a reciprocating engine, you've got all the stuff going on inside of this. You've got pistons moving up and down. You've got the ignition at the correct point. You've got exhaust coming out at one point, and an exhaust. The intake goes into the engine. You've got all this stuff going on inside this engine, inside of a constant flow cycle engine or Brayton cycle engine. All of this is happening simultaneously. So this is a turbine engine we're talking about here. So you're going to have a compressor that squeezes the air, compresses it down. You're going to add heat to it by adding fuel. We introduce that fuel to it. What happens is that combustion of that fuel raises the temperature and the pressure even more. You're going to duct that hot gas that we know is exhaust over a turbine wheel. When it goes over the turbine wheel, it's going to turn the compressor up at the front of the engine. So as long as this thing has fuel, it's going to continue to run. Right? It's a real simple engine. The temperatures are very stable inside these engines. They're hotter than they are inside of a reciprocating engine, but the temperatures are very stable. The engines are built to withstand that. So you have to write any of this stuff down. Right. We're going to skip through this real kind of right here. Know that the turbine is connected. This part right here is connected to the compressor through a shaft through the middle of the engine. And as long as this turbine is being fed hot gas and it's spinning, it's going to turn the compressor up front. The compressor is going to draw air in. It's going to squeeze it down. We're going to put it in this area here. We're going to expand the gas. raise the pressure, add fuel to it, and as that fuel burns, that hot exhaust gas goes back over the turbine. So we're playing a bunch of aerodynamic tricks inside this engine. You go to the turbines class, we'll talk about that at some length. Okay, so you can read that or not. It's up to you. Next thing, manufacturers. I'm gonna be done here at 7. Kind of hurrying you along. You don't have to write any of this stuff down. I just want you to know there's a bunch of different manufacturers for these gasoline engines. We're back to gasoline engines now. Allison built engines, mostly during the World Wars until right after, probably about the 50s and 60s. No longer build engines, now they build gas turbines. Bombardier Rotax. Rotax engines are still in business for aircraft. They build a lot of other different engines for snowmobiles and utility vehicles. Fairchild Ranger, no longer in business. They build an inline engine, that is to say 4 and 6 cylinders inline with one another. It was an inverted engine, so these cylinders hung down below the crankshaft. They were upside down. Franklin built engines like Lycoming and Continental, like what we have outside there. They're no longer in business. This is kind of a cutthroat deal. Franklin didn't build particularly robust engines. There was a lot of mechanical issues with those. Ladd and Kinner built small radial engines. And these are engines that have the cylinders arrayed around the crankshaft. So I pointed a couple of them out to you last week when we were outside. A little bit different shape, kind of antique engines, no longer in business. Jacobs, another company, no longer in business. Now, I don't mean to tell you these engines aren't still around. There's a lot of them still around. A lot of them are still in service, and so if you work on small aircraft, there's a very good chance you get mixed up with these. Porsche still builds engines for blimps. They built some engines for some small aircraft, some Moonies especially. They're beautiful engines. They're gorgeous. But they were so expensive, nobody could afford them, so they didn't do that anymore.
What was the PFM?
What's that?
What was the PFM for?
Yeah, because they're so bitchin'. They're bitchin' engines. Yeah, they're really nice. They had too many features on them that were complex, and so they ended up being too hard to deal with by most shops. They had to have shops that had special tooling, and people had to be trained accordingly. So what was happening is there were probably 500 Moonies built with those in them, and so of course all the Porsche guys they all had to have one. If you flew an airplane, you were a Porsche guy, you had to have one of those too. Yeah. But they were pretty expensive to work on as well because of all the magic involved. Pratt Whitney, still in business, build turbine engines now, no longer build the radials, but thousands and thousands and thousands of these things still out there going to work every day on aircraft. Teledyne Continental still builds quite a lot of air-cooled closed engines. They have one that's liquid-cooled as well. They don't build the Boncos anymore. They do build turboshaft turbines still. Textron Lycoming probably builds 7 to every 3 that are built by Continental. Same type of engine. They're used on a lot of small aircraft. They also build some turboshaft engines for industrial power plants, and they build a small turbofan also for a small airliner.
You said that Franklin used to build Lycoming?
What's that?
Did you say that Franklin used to build Lycoming?
No.
No.
No. Franklin, it was a company unto itself, and their engines weren't that reliable. They kind of just, people stopped using them. They just kind of went out of business. Warner, it's more small radials like Kinner. Wright makes machine tools now and components for heavy jets. They're no longer building radial engines.
What was the second one about?
What was that?
Previous slides, the cyclones.
Yeah, that was one of the names of one of their engines, so they had a number of engines in the Cyclone family.
The Cyclone family was the biggest competitor to Pratt & Whitney's
Pratt
Wasp
for
family.
years, yeah. So there's this one here, I'm not even gonna tackle that, and it's a Polish company, they own Franklin, they own the tooling for Franklin, so you can still buy parts for Franklin, though it's a little bit hard to get. They're still around. They build radial engines also, they bought some of the tooling from Pratt & Whitney, so you can still buy some of the parts if you need them for Pratt & Whitney radial engines. Alright, so here you go, now you're gonna write again. We're almost. Alright, so some of the early engines, when they first started coming out with engines, they didn't think about using the cubic inch displacement or the size of the engine as a way of identifying engines. So what they did was they used the horsepower that the engine would make. So in this case, an A65 was built by Continental, and C90 was built by Continental. So it's A65 horsepower, 90 horsepower. The E225 was 225 horsepower. And then there was a military version of one of these engines, and it was a 684-165-P3. It kind of rolls off the tongue, right? But the thing here is that it was 165 horsepower in that case. Now all the engines have gone to a newer system, and that's cubic inch displacement. Bring that back for you. And this is the amount of air, theoretical amount of air, that would be displaced by the piston movement. You should probably write that down. The theoretical amount of air displaced by the piston movement. So you know the piston is going to be all the way at the top. So you start from that point, right at the top of the piston. And the piston goes all the way down to the bottom. So that's going to give you a volume inside that cylinder, from the top of the piston at the top to the top of the piston at the bottom. Doesn't include the combustion chamber. All it includes is the amount of air that the piston would move in one stroke. Okay, one stroke. So you've got the area of a circle times the length of the movement, right?
4 times 2.
Okay, everybody okay with that? Because we're going to do some compression ratios, and you're gonna have to work that out. So think about it. How many of you love math? Nobody's hand.
My calculator.
So it's a pretty easy calculation. You're just going to measure, find the area of a circle. Right? Full story, pi r squared, pi r not squared, pi r round. Stupid, right? But you're going to remember it. Pi r squared. That's your formula for finding the area of a circle. And then you're going to go by the stroke, or the length of the piston movement. Multiply those two together, and that gives you the cubic inches of air that piston would theoretically displace. Now, it doesn't happen that way because air being what it is, sometimes it's more dense than other times. Sometimes you have the draw of the piston. The piston starts to draw, it's like sucking on a straw. You don't get your Slurpee doesn't come right up the straw, so you start sucking on it. There's like this little delay, right? You all would agree with that? The green berry doesn't, or the blue berry doesn't come up the straw all that fast, right? And that's what happens inside the cylinder. So the cylinder starts sucking to draw the air in. Well, there's not that instantaneous begin to fill going on. So there's going to be a little bit of slack time in there where the suction begins to get a grip on that air and starts drawing it in. So it's not 100% efficient, but what we use this mathematical cubic inch displacement. Now the other thing is you're going to see when we start figuring these out is that the marketing guys kind of get a hold of these things. So you know, mine's bigger than yours, right? So if you end up with, you're going to find each cylinder maybe has like 90.3 cubic inches, and you got 4 cylinders. Somebody with a calculator, you got a calculator, run that for me times 4. 90.3 times 4. What's that?
27.
Is it?
361.2.
361.2, sounds a little high.
Mhm.
That's okay. That's all right. So what the guy in the marketing department is gonna say, well, who's gonna buy an 0361.2? So they're gonna round that number. So they're gonna say it's 0360. That's what you're gonna find out. So these numbers will be high or low off of that. And so what you're gonna find is that if I give you a problem, I'm gonna give you a number for an engine, and I'm gonna give you you're gonna have to figure out the actual amount of displacement on the engine. So Lycoming makes, and Continental both do, they make an 0360. It's an opposed engine, cylinders, pistons go this way, and each cylinder is about 90 cubic inches. So you got four cylinders, and then you're gonna multiply that by each cylinder, and that gives you the total displacement on the engine, not by cylinder, but by total displacement on the engine. So if the marketing guy says, oh, we're gonna sell an 0360, we can sell millions of them. If we sell this as an 0361, nobody's gonna remember that. So that's what
This is the Ducati 998 or something.
what's that?
This is the Ducati 998 or something like that.
Yeah, you end up, some of that stuff, it sounds hip, but most people just look at this and I gotta remember those other numbers. Okay, so the numbering systems, here we go. So, we've got all these other numbers here, and I'm gonna break this down. You don't have to write these down if you don't want. I just want you to see, what some of these letters and numbers, when they crash together, because you've got these on your engines outside, and most of them are exposed. But, so you could have any one of this alphabet here, followed by the 540. 540 is the displacement on this engine, 540 cubic inches. And then you have some suffix letters, SUFFIX, suffix letters, A1, A6. Now, these are things that can mean things like what kind of magnetos the engine has on it. It could tell you what the gear train is. It could tell you whether it has a hydraulic pump. If you look in the codes in the maintenance manuals, Landis showed you guys the maintenance manuals yet?
Yes.
Okay, so if you look in the codes for the maintenance manual, it tells you what accessories are attached to it. It might tell you that the thing has a gear reduction on the front of the nose. It might tell you what kind of crankshaft it is. It tells you all kinds of stuff. But this alphabet business here, well, let's just go on here and we'll do this. So F means it's fan cooled. H or V is for a helicopter. V is for a vertical engine, an engine that sits upright. So you saw it start to kind of make sense a little bit. So you can or not write these down, but do it quickly because we're humping along here pretty quick.
So what's the H for?
Helicopter.
H is for helicopter.
Okay.
L is for a left-hand
Left-hand
rotation.
rotation.
So when you're sitting in the pilot's chair, most American engines turn this way to the right, or clockwise. A left hand would go the other direction. The reason you might use that is because you have a twin-engine airplane. And so you'll know about gyroscopic precession. So if you have two of them going the same way, this airplane wants to roll over like an old dog if you lose one engine. If you have engines that are counter-rotating, now one tends to offset the other. Okay? So that's why you might have a left-hand rotating engine. A would be an aerobatic oil system in the engine. So that means that the engine will continue to run upside down, undamaged, because it has an inverted system. Geared. So the engine might run a little fast for the propeller, so they gear it down. So if you run an engine a little bit faster, you get more horsepower out of it. Just that simple. So 2,700 RPM is pretty standard in an aircraft engine. But if we push it up to 3,200, so our 300 horsepower engine now is putting out 385 or 400 horsepower. So you get more horsepower out of it just by speeding it up. You have to a little bit of extra complexity because now you got a different crankshaft, you got a gearbox reduction on it, you got to make a different crankcase. But if I can sell a bunch of those airplanes, I'm going to do it. T, turbocharged. S, supercharged. Two different things, very close to one another, but two different things. Injected. fuel. Who's got that TIO 540 back there? So what does that TIO mean now?
Turbo injected.
Opposed.
Turbo injected opposed 540 cubic inches. Yeah. So you see where this is all going here now?
And then over there, there's a GTSIO 520.
There's a GTSIO 520 on there also. Okay, so opposed, or R for radial, or I for inline, V or mill radial. There's all these little other alphabet letters here. And then the cubic inch displacement on this engine, we looked at that, and it's usually around to the nearest 5. Remember, the marketing guys kind of take over at that point. It's not necessarily what the engine is, it's just what sounds good. And then you have the suffix letters, so this could be the models and the modifications to your particular engine. So some of these engines were just built for simple little dinky airplanes, and then maybe they were used as a second engine on a twin engine airplane as well. So, or a first and second engine on a twin engine airplane, in which case they would have different suffix letters on them. Okay, so we have this O540 E1B4D. It could be modifications about the engine case. Some of these engines have different engine cases within the family of engines. The nose section, maybe it has a gearbox on it, and the accessory section, maybe it's built a little bit different from one other O520. Counterweights, magneto arrangements, all of those things are going to enter into the suffix letters. You can find that in the maintenance manual, what those suffix letters for. Okay, so we're going to quit there today. I know it's kind of boring stuff. Some of it's just mind numbing, in fact, but you got to get it. You got to know it. So tomorrow, I'm going to send a text to Linda and have her allow you guys to take your accessory sections off tomorrow. All of that stuff, typically it's going to be a bring a 12-point, bring yourself some 1/4-inch drive